So a simple special case is that p, assume that p greater than 0. Next step. So this you can think of as step 1. Okay, this is a nice lemma, right? You can think of this as step 1, but it's not quite enough, right? The next step is for you assume p greater than 0. That means that Pij is greater than 0 for all ij equal to 1 to m. So we are looking at now a complete directed graph, meaning that you can go from any state I to any state j with strictly positive probability, right? See, this kind of Markov chain is of course ergodic, right? But this is this is a very special case, right? You are necessarily demanding every transition from every pair of states to is possible, right? You can go from any I to any j for any I and j. This is a stronger assumption, but this is a very nice case, all right? So if this is the situation, right? For this case, you can have you can prove the following: max over I Pij n plus 1 minus min over I Pij n plus 1. So let me define, so we are going to show that the max minus min actually goes down geometrically fast. So let me define, let alpha equals min over I comma j, min over I comma j Pij. Okay, so this alpha is greater than 0. Remember that each Pij is strictly positive. So if you go over all the columns and all the rows, look at the smallest element of your transition probability matrix, that will still be a strictly positive number. You call that number alpha. Alright. So what we are going to say is that if you look at this difference, max minus min, alright, is less than or equal to max so if n becomes one bigger, the difference between the max and the min reduces geometrically fast. 1 minus alpha, 1 minus 2 alpha. Okay, so this 1 minus 2 alpha is some number less than 1, right? So the difference between the maximum entry and the minimum entry in the n plus 1 step transition probability matrix reduces by a geometry is a multiplicative factor of 1 minus 2 alpha compared to the difference between the max and the min in the n step transition probability. Alright, so this implies that, this we have to show of course, this implies that if you look at this max minus min, this guy goes down geometrically fast. So these both are true for all states j and for all n greater than or equal to 1. Okay, so this is a a very strong statement, right? So if you have every entry positive, the max minus min, right? The difference between the max and the min in any column goes down geometrically fast as n increases. All right. So as n tends to infinity, the difference between the maximum and the minimum goes down to 0 exponentially fast. So you must have a convergence, right? So this also implies limit n tending to infinity max over L Lj n is equal to the limit n tending to infinity min over L PLJ n. Okay, and all of this will be some. All of these will be greater than or equal to alpha because the entries are all greater than or equal to alpha, and this will be greater than 0. This also we can prove. Okay, alpha is of course greater than 0, right? So in this case, so in the previous lemma for any finite state DTMC, we proved that the max over any column keeps decreasing and the min over any column keeps increasing, right? But as n tends to infinity, it's possible that they may not actually converge, right? There may still be a gap, right? However, when the P matrix is strictly positive, each entry is positive, this gap goes down exponentially fast, geometrically fast, right? So the max and the min converge to the same limit, all right? And this will obviously be some function of j, right? And in fact, that will be your pi j. Okay, so this is something we can prove. Okay, so in this special case, you can prove that p to the n converges to some pi j, right? So just to walk you through how this is proved, if you go to again I'm going back to this Gallagher's book. Okay, so this is the statement of the lemma, right? You are looking at transition probability matrix. It's each entry strictly positive, right? And you are looking at the max minus min of the n+1 step transition probability going down by a geometric factor 1 minus 2 alpha, right? This is what I stated. The proof of this is also somewhat just algebraic and elementary. So let me just walk you through that. So you write out the Chapman-Kolmogorov equation. This is just Chapman-Kolmogorov. Okay, and so you're replacing. So this sum you're just leaving out the L min term. Okay, where L min is the value of L for which PLJN is minimized. Okay, so you're just taking out one term out here of the sum, and then you're basically in this step you are adding and subtracting this particular term. All right, this is just again some algebraic Jableli, and so this PL min. So this P I L min, right? L min is the index where the minimum occurs, will be greater than alpha, right? So which means that this inequality follows. Okay. So and similarly, if you manipulate for the min, right? So this is for the max. Similarly, if you manipulate for the min, you will get this inequality. All right. These are just algebraic steps. Okay, so you can just subtract the two, and from these two inequalities, you can just get the first inequality that you wanted to prove, that there is a geometric reduction in the difference. Okay, and then from monotonicity and the fact that the gap is decreasing exponentially fast, you can prove that the limit there is a limit and the limit is strictly positive. So this is for a Markov chain in which all the entries are strictly positive, right? So, but that is too strong an assumption, right? In fact, we want to prove that p to the n converges to pi for any ergodic unichain, right? But this is we have assumed that all the states between any two pair of transition between any two pair of states is possible. That's too strong an assumption. So in step 3, we will relax this assumption, right? So you look at a ergodic chain. Okay, so ergodic chain means one aperiodic recurrent class plus no transient classes. Okay, we will put the transient classes later. Okay, so we are going from p strictly greater than 0 to p corresponds to a single ergodic class, okay, and no transient classes. So for this, recall that for such a ergodic chain, p to the n is strictly greater than 0 for n greater than or equal to m minus 1 whole square plus 1. So this is a result that we stated, I think, a module or two ago. If you, in an ergodic chain, you can go from any state to any other state with positive probability in a finite number of steps. Okay, especially for so if you take n greater than this m square roughly, then the matrix p power n, the n step transition probability matrix, will have all entries strictly positive. All right. So what we are saying is that the matrix P may not correspond to a complete directed graph, meaning that some transitions may not be possible. But for n large enough, the n step transition probability matrix will have strictly positive entries, especially when you take n greater than or equal to this m minus 1 square. So let me call this number equal to some h. All right. Now what happens is that if I take so you take the matrix, approach is the following. Take the matrix e to the h and apply the result from step 2. What does that mean? This matrix has strictly positive entries, p to the h, right? So to the matrix p to the h, you can apply the result that we proved here, right? That for the matrix p to the h, if you take p to the h to the n plus 1 and p to the h to the n, then this result in your screen will apply, right? So p to the h will satisfy this result. Correct? So from this you can work back and prove something for P itself. Alright. So what you can prove is the following. So so this is the matrix P to the H is strictly positive. Let beta equal to min over I comma j Pij h. Alright. So Pij h is strictly positive, right, for every ij, and you're looking at the smallest entry in the p to the h, and so the beta is strictly positive. So for this beta, you can state a similar result. So if you look at max over I, so this can be a lemma. Okay, so this is a lemma for ergodic chains. Okay, max over I, Pij to the h times n plus 1 minus min over I Pij h plus 1 is this not equal to the same thing with m plus 1 replaced with m, right? Hn minus min Pij Hj. Okay, so we are just pretending that Pij h has they are all strictly positive. So we are looking at the matrix P to the h and applying the same result. So this times 1 minus 2 beta. This is exactly what we know from step 2, right? We are applying the step 2 lemma, right? So on this implies that this max over L PLJ HM minus min over L Eij Hm, this goes down exponentially fast. So this will be like 1 minus 2 beta whole to the n, right? And therefore you can prove that limit m tending to infinity max PLJ Hm is equal to limit m tending to infinity PIELJ Hm is some number which is strictly positive. Okay. Yeah. But we know that max over I. So we are now going to the limit along Hm, right? We are not able to say limit n tending to infinity, right? So we are looking at a subsequence like Hm, and along that subsequence we are able to show that there is a limit, right? But we know that max over I Pijn and min over I Pijn are both monotonic. Correct? They are both monotonic. This is the first step we proved, right? And therefore, these guys must have a limit as n tends to infinity. And that limit must be equal to the limit along the particular subsequence Hm, right? So then your result follows, right? Dot dot dot. So if you can just, this is also there in Gallagher. If you look at this this bit on ergodic Markov chains, so you're looking at for any h greater than or equal to that much, you're guaranteed that p to the h is positive. I've just taken h equals m minus 1 square plus 1. So for the matrix p to the h, you can apply, this is all from step 2. I'm blindly applying for the strictly positive matrix p to the h, I'm applying that result. So this limit along this subsequence Hm, this subsequence Hm, I must have the limit, right? But then I have monotonicity, this non-increasing and non-decreasing in n property of Pijn, max and min of Pijn. Therefore, you can have, you can just prove that if you go along any n, you must have a limit. And further, the max and the difference between the max and min goes down exponentially fast, like so, right? So now that this limits exist, you can just define this common value of limit of the maximum and limit of the minimum to be some pi, all right? And finally, we end up proving that since this pi j lies between the max and the min over the various i's, we must have Pijn, the absolute value of Pijn minus pi j, goes down exponentially fast. So this is perfect, right? So for an ergodic Markov chain, this equation 4.22, which I've just arrived at using this strictly positive matrix p to the h, we have proven this crucial equation 4.22 that Pijn, the n-step transition probability, minus pi j, which is that limit defined above, goes down exponentially fast in n, right? So not only do you have convergence of Pijn to some this pi j, the convergence is exponentially fast. It's geometric in n, right? So you have that limit, and this limit is approached in a geometrically rapid manner. Okay. So we have proven that for a ergodic Markov chain, basically a Markov chain in which there is all the states there are recurrent and aperiodic, then we have p to the n converges to this pi. All right.